So now we have this, in the generalization of quantum mechanics to various variables, we have this generalization of the fermionic algebra. Now we want to construct the vacuum. So the vacuum is defined by a state which is annihilated by all the annihilation operators. So this is what defines the vacuum. And then on this vacuum, we can act with the creation operator. So before, we had one single operator, so we can only create one state, but now we can create many states, because first of all, we can create the states acting with one single fermionic operator. But it's clear that now we can act with two fermionic operators. Before, we couldn't act with two because there was only one fermionic operator, which is nilpotent. So if we act twice with the same fermionic operator, we get zero. But by now, it should be clear that you can now act with different fermionic operators and construct this new state. And notice, of course, as the xi is anti-commute, there is only really one linearly independent state, which corresponds to I bigger or equal than 1, strictly equal than j, smaller or equal than n. Because if you, so we can order the indexes here, because if you exchange the indexes, you just get a minus sign, so with the same state. And then you can go on and you can add with three fermionic operators, where now you have 1 less than or equal than I, less than strictly equal than j, strictly equal than k, strictly or equal than smaller or equal than n, and so on. And the last state that you can form is with n fermionic operators, and this is the state xi minus 1, blah, 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 psi minus n acting on 0, okay? So this is the structure of the fermionic states that you can generate, and there are various things that are interesting. The first thing is that remember, this is very similar to the structure of the polynomial ring in Grassmann variables. Huh? So there are various observations that I want to make here. So the first observation is that there are in total 2 to the n states, right? So, because, you know, this is 1 plus n over 2 plus n over 3 plus 1, okay? And then the second thing that I want to emphasize is that these states look very much like a basis of differential forms on Rn, right? So if you think about S plus I as the analog of dxi, then, you know, psi minus I, psi minus j is the analog of dxi. So you wedge dxj and so on. So this is a parallelism that we have already made when talking about Grassmann variables. So we mentioned that the polynomial algebra in Grassmann variables was isomorphic to the algebra of differential forms. And this is something that we will also use a lot in this discussion. So, of course, the last one is proportional to the volume form. Okay. Okay. So this means that now the Hilbert space that we're going to have is interval functions on Rn, and then we will have to tensor with all these fermionic states, which are going to be 2 to the n copies of C. Okay. Very good. So this is our enlarged system, and now we have to construct a Hamiltonian. So our Hamiltonian is an operator which it's going to be a slight generalization of what we did before. So it will have a standard kinetic part pi a squared. Then we will have a part like this, which involves the gradient of a function h to the square. So this is the bosonic part. So H is a function of X, and then, it's promoted to a function of the operator X hat. So I should put a hat here to indicate that these are operators. And then there is a fermionic part in which you sum like this. So the I, J, H, and then we'll have here psi minus I and psi plus J. So this is a generalization of the Hamiltonian we have in the one-dimensional case. And in the one-dimensional case, we wrote this Hamiltonian in terms of a function omega of X. Here we are using a function H, but when n is equal to 1, we recover this previous construction by setting H equal to minus omega prime of X. Okay? So if this is the case, here we have omega prime of X to the square, and here we have omega second of X with a minus sign. And this is because before we put the commutator in a different order. So the minus sign is just a convention, which is going to be useful later on to make the connection with Morse theory, okay? Okay, so now I lost the connection of the iPad. So okay, so now we have to I mean, if we want to have a supersymmetric quantum mechanical system, we'll have to construct supercharges. So the supercharges are going to be given by Q plus minus is equal to psi plus minus I, and then Pi plus minus I di H of X, okay? And it's easy, relatively easy to check, and this I leave it as an exercise for you, that H is actually 1/2 of the commutator. So this is something that we used before. Then, so H is the anticommutator of the two supercharges up to a factor of 1/2, okay? So this is a slight generalization of what we had before. And we can now study this Hamiltonian again, as we did before. So what we are going to do now is just to repeat one part of what we did before. And this part is the perturbative analysis of supersymmetric ground states. So this is a multidimensional system. So in principle, it's more complicated to do this, to do an exact analysis, but we can still do our perturbative analysis. And this is very similar to what we did before. So remember that the basic idea when we were analyzing the perturbative ground states was to look at the bosonic part of the Hamiltonian and say, well, if we want this part, this is the momentum, this is the potential. So we want to have an approximate ground state in the classical theory. We can take, we have to look at places where this potential has a minimum. So in this case, it means that it vanishes. So one way to actually do this is to assume that we rescale H to lambda times H, and then we take lambda very large. So in this limit, the states which have a non-zero, so this term here scales to lambda square. So we see that every point that doesn't lead to a zero of this function will have a large energy. So we can think about lambda as some sort of coupling constant, and we are going to do an analysis when lambda is large. But we'll see later on that the structure of supersymmetric manifestation depends on lambda. So this gives you some way of calculating the energy of states when lambda is large. Okay. So approximate ground states when lambda is large are going to be located at the places where this function, it's the first derivative of this function is 0, and these are called critical points of H. Okay. So what we have to do is to expand this function around this critical point. So we are going to assume that this is a discrete set, that there is a discrete set of critical points, xi. So this means that di of h at xi is equal to 0 for all I. And I is an index labeling the number of critical points. We are going to make the important assumption that if you now expand h around this point, you will have h of xi. The first derivative is 0. So I'm going to use the Einstein conventions with respect to repeated indices. So we have this plus higher order. And we are going to assume that this second derivative matrix, which is the Hessian of this function, which I'm going to call like this, so this is sometimes called the Hessian of H at xi. We are going to assume that this matrix is invertible. And at the critical points. And so in other words, this is what is sometimes expressed by saying that H is a non-degenerate function at xi. Now, a function which is non-degenerate at these critical points is called a Morse function. Okay. So these are the functions that are used in Morse theory. We are now working on Rn. We are going to extend this to a general manifold later on, but so far this is already the kind of properties that you require in the study of Morse theory. Okay, so let's go back. So we have this Hamiltonian, and we want to analyze it near the critical points of H, because this is where the approximate ground states are going to be located. And we have to expand this around these critical points, like what we did before. Remember that before we did a similar analysis in which we essentially express the Hamiltonian as a harmonic oscillator plus a fermionic piece. Now we will have to do the same. There is a standard part of this story, which is that when we expand this function around around the critical point, you see we will get a complicated matrix. And the standard procedure already in classical mechanics is what is called to go to normal modes. We want to diagonalize the quadratic fluctuations around the minimum. Okay, so this is a standard procedure. This matrix is symmetric and is invertible, so we can diagonalize it. I mean, being symmetric, we can diagonalize it. So let me write this matrix HI, and I can diagonalize it by an orthogonal transformation like this, where A minus is equal to AT, and CI is a diagonal matrix, which I'm going to write like this. And all these I are different from 0 because of the assumption of H being non-degenerate at the critical point. So there cannot be any zero eigenvalue here, okay? Now it's now a very easy task to diagonalize the fluctuations. So the fluctuations, I mean, we want to do this. Remember that we want to do this because we are actually working with this Hamiltonian, right? So we want to do this exercise. So if you want, if you write the DAI-H and you span it around the critical points, you will get DI-dJ of H at xi times xi, oh, sorry, xj minus xji plus higher order. So when we take the square of this, we are considering then this matrix. We are considering the matrix. So if you write this in, so let me write this, just some notation. Let me write this as delta x, okay? So this is going to be given by delta x h square delta x, okay? So if we diagonalize, so we want to diagonalize this expression, okay? So the way to do this is very simple. So we are going to introduce normal coordinates. So this is really a trivial exercise, not even in quantum mechanics, but in classical mechanics. But let me do it in some detail, just in case you're not used to do that. So remember that I can diagonalize H with an orthogonal transformation. So I can now introduce normal coordinates around each critical point. So this depends on the critical point. So this is A, I, J, xj minus xj I. And then, so if you want in matrix form, this is psi is equal to A times delta x. So it's clear that this fluctuation, I can write it as, so I can write delta x as A minus 1. By the way, this is the transport matrix. So A minus 1 psi. So if I transpose here, I will get psi I transpose, and then A minus 1 transpose, but A minus 1 transpose is A times H squared times delta X, which is A minus 1 psi I. But now I use the fact that I can diagonalize this matrix, so H squared can be written as A minus 1 Ci times psi I squared, because I'm squaring H. So this is Ci squared times A times A minus 1 times Ci. And then you see that this is 1, this is 1. So by doing this, I have an expression in terms of so this is the transpose. So this is very nice because this is just the sum over I1 n of Ci I Ci I square. So now the potential part of the Hamiltonian has now been analyzed in terms of n harmonic oscillators, and DCI play the role of a square, by the way. Oops. So let me write this. I have to square this because the matrix is a square. So this is C I square. Okay. So this plays the role of omega square in a harmonic oscillator. So we have a bunch of harmonic oscillators whose frequencies are obtained by squaring the eigenvalues of the Hessian. Okay, good. So now this is in what concerns the if you want, the bosonic coordinates. But if we look at the, I mean, we also have to diagonalize the momentum, but it's also very easy to see that we can do a linear transformation of the momenta by the same matrix, IAJ. And if you do this, then the normal coordinates, you know, the operator version of the normal coordinates satisfy the Heisenberg algebra with this rescale moment, with this linear transformation of the momenta. So this is very easy to verify, just using that A is an orthogonal matrix. Okay, so since this is an orthogonal matrix, the bosonic part of the Hamiltonian is going to be written like this, plus Ci, sorry, just using the bad notation. So this is Psi I square times Xi I square. So the bosonic part of the Hamiltonian near a critical point is going to give approximately by this expression. So it's just, as I said before, it's a bunch of harmonic oscillators with frequencies given by the eigenvalues of the Hessian. Okay. So the last thing we have to do is to analyze the fermionic part. And again, you can imagine that we have to do some similar trick. So the fermionic part, remember, was di djh x minus I x plus j. But this also involves the Hessian, right, of this function. So when you are near a critical point, and I'm already going to focus on this, you can just write this in this way. And we would also like to diagonalize this in a nice way. So in the same way that the Hamiltonian in the bosonic sector was a general quadratic form, we wanted to diagonalize this. Here, the Hamiltonian in the fermionic part of the Hamiltonian will be a quadratic form in the fermionic operators, and we want also to diagonalize it. And it's very easy to see that the right diagonalization is simply to use the same orthogonal transformation again. And this being orthogonal doesn't change the anti-commutation relation. So these new fermionic operators anti-commute in the same way. But now we can simplify a lot this expression, because this is a one-line calculation, but it's worth doing it. So if we change the definition of, let me just make sure that I'm not, actually, yeah, probably this is the other way around. Okay, that's the other way around. Okay, so if I do this, what I get here is IAK, IJL, and then I have this new operator, so K plus, sorry, minus psi L minus. And now this is so let's see. So this is A. Okay, so maybe I want to do this. So sorry, one has to just make sure about these things here. So actually, let me go back to this. Yes, and let me just put this the minus the. So if this is this, I can just change here the inverse matrix. So let me just do the inverse matrix. And then here, if you see how the structure of this, you can see that you have here A minus 1 transpose Ki H I J I times A minus 1 JL, and then we have S minus S plus. And then we have diagonalized this because, this is this matrix here is A minus 1 HA, but A minus 1 HA, no, this cannot be, no, sorry, this is A. This is A minus 1 transpose, which is A. So we have this. And remember that this was A minus 1 CI, or CI upstairs. Here, A minus 1, so this is CI, okay? So CI is diagonal. So the whole thing here gives me just sum over 1 I of n of C I times C hat I minus C hat I plus. Okay. So this is how you diagonalize the fermionic part. So now putting everything together. So I have this is the bosonic part of the Hamiltonian. So I have this, and then I add this thing here. So now the Hamiltonian, the total Hamiltonian, is a sum of one-dimensional Hamiltonians. In the sense that here only it's a sum of, I completely decoupled all the modes, both bosonic and fermionic. Now remember that I can always represent this. Now, since I have a one-dimensional Hamiltonian, I can use the representation of the algebra that I had before, and then I can represent psi 1 minus psi I plus by the matrix minus sigma 3. This is very easy to see. In the same way that we're using the opposite, we're representing the opposite commutator by plus sigma 3. So at the end of the day, I can go here and I can replace this by can just forget about this and put a matrix representation. Okay, and I give, you know, this gives me the Hamiltonian that I had before. Now, this Hamiltonian we studied in detail before. It's very easy to see again what you get. So each of these is a harmonic oscillator, and we are interested in the ground states. So the ground states depends on the sign of these frequencies. This is also something that we already saw before. So so the only thing is that we are using the opposite convention for reasons, you know, for reasons of convenience in order to compare to Morse theory. So what we have is the following. If well, determining the sign is very easy. So this part of the Hamiltonian will give you an energy which is this one, and then, well, let me put h bar equal to 1. There is an h bar here if you want to put all h bars, but no, let me just put h bar equal to 1, which is actually what we have been doing. And then I have this thing here. So it's clear that if this frequency is positive, then you can see that, remember that this, you know, this is a matrix, right? This is the matrix CII minus CII. So if this is positive, and in order to have zero energy, you have to use the upper entry here, okay? So you have to use the bosonic sector. So the vacuum is bosonic. And if CII is negative, the vacuum is fermionic. And from the point of view of the structure, you have you will have to add with you know, it's the vacuum which is obtained by this orthogonal or this orthogonalized operator sign minus acting on the vacuum zero. Okay, and this is for each I. Okay, so what is the consequence of all this is that when you put into account all the oscillators, the vacuum, I mean, the bosonic structure of the vacuum will be just a bunch of harmonic oscillators picked around the critical point. But the vacuum, the fermionic structure will be a product of all the I's such that Ci of I is negative with Ci minus acting on zero. Okay. So the number of fermionic operators here is the number of negative eigenvalues. In Morse theory, there is a number for this. So the number of negative eigenvalues is called the Morse index of the critical point. Okay, and then you see that this is exactly the number of fermionic operators that appear here. Now, why this is interesting? Because one thing that we want to know when we look at a vacuum, it's its fermionic number. Remember that there is this operator F that counts the number of fermions, and in particular, there is this operator -1 to the F that gives you the Z2 grading of a state. So it's clear that the vacuum, well, let me call it the approximate vacuum that we have obtained it's an eigenvalue of this operator. It's an eigenstate of this operator with, let me call the Morse index mu I. And the eigenvalue of this operator is -1 to the mu I. Okay. This is what I'm saying is essentially trivial. I'm saying that if we have a critical point with Morse index mu I, which is the number of negative eigenvalues, then the vacuum will have fermion number mu I. And in particular, -1 to the F will be -1 to mu I. So this is an approximate analysis of ground states. And we know already from the analysis of quantum mechanics that not all of these approximate ground states have to be true ground states. So we might overcount supersymmetric ground states in this way. But it's very important to remark that we are not undercounting supersymmetric ground states. So if a state, if I find an approximate ground state, it might happen that in a full treatment of the theory, I get a non-zero energy. Okay, so these are states which have approximately zero energy in perturbation theory. And this is at all orders in perturbation theory. And you will do an exercise for the supersymmetric double well, where this will be shown. So these states have zero energy in the perturbative expansion. They might get a non-zero energy from non-perturbative effects in quantum mechanics. So we might be overcounting supersymmetric ground states. Now what is clear is that if a state is supersymmetric, if a state is truly supersymmetric, it must be one of these approximate ground states. So I'm not really undercounting, because if a state is not here, this means that already at the perturbative level has a non-zero energy. So there is not going to be any mechanism that is going to remove that energy. Okay. So if a state in supersymmetric quantum mechanics has zero energy in perturbation theory, it might not have zero energy exactly. But it's clear that if a state is supersymmetric, then it must have zero energy at the perturbative level. So, and might be overcounting supersymmetric ground states in this way, but I'm clearly not undercounting. Okay, and this is going to be probably important later. Another consequence of this analysis is the following. Remember that this approximate analysis of ground states is approximate, but it's already good in order to compute the Witten index, because the Witten index, it doesn't really depend on the details of the theory. So we can compute it by doing an approximate calculation of approximate supersymmetric ground state. So this means that trace -1 to the F in this theory is actually given by a sum over critical points where we count its Morse index. So that's a beautiful formula. And this formula will be very important when we actually put this theory in a supersymmetric, in a Riemannian manifold. Okay. So I think we can stop now for this moment with this part of the course, and I will we will come back in 10 minutes or so. Now, very importantly, are there any questions? This is not completely trivial. Huh? So let me say that many of these things were invented by Witten. I actually encourage you to read his papers on the subject, which are very beautiful. So the first one is called Dynamical. I mean, maybe you are not able to read all of them, but.
Marcus, sorry, is it possible that your screen froze?
My screen is froze. Oh yeah, maybe now, yes. Yes, okay, sorry. Let me stop the share for a moment and then let me do it again. Oppa, tac. Yes, so this is the formula that it was not there. So as I said, this is just an application, what we did, because as I said, all these critical points have -1 to df given by this, and then we get this beautiful formula. So let me say that many of the things I'm saying were invented by Witten in a quite amazing set of papers. So 2 physics papers, constraints on Susy break, dynamical breaking supersymmetry and constraints on Susy breaking. And then a math paper, which is called Supersymmetry and Morse Theory. And I really encourage you to have a look at these papers because, with what we explain in the course, you can read most of them. I mean, everything I'm saying was just invented by Witten in these papers. And he was interested in supersymmetry, but he realized precisely by looking at these simple examples that in supersymmetric models involving this function h, you can characterize the supersymmetric vacuum, or at least the approximate supersymmetric vacuum by these properties of h. And then he went on to relate this to Morse theory in a very non-trivial way. As I said, what I have explained now is that essentially if you will have this supersymmetric quantum mechanical model, right? You will have this supersymmetric quantum mechanical model here involving a function h. And if you assume that h is a Morse function, so it has a discrete set of critical points where the function is non-degenerate, then the approximate, the calculation of the supersymmetric Canova states in perturbation theory gives you immediately this kind of quantities related to Morse theory, the sum over -1 to the Morse index and so on. So this emerges very naturally from this. And as we will see, this way of deriving the main results of Morse theory from this point of view of supersymmetry. And this was for me, a very striking application of ideas of physics in mathematics, which eventually led to a new point of view on Morse theory. Okay. Anyway, we will explain this in the second part of the course. So in 10 minutes or so. Are there any questions? No? Okay.
Can we discuss our schedule again? Because as SwissMAP told us, our term ends on the 29th of May and exams start on the 8th of June.
Okay, for me it's okay. I mean, we can do the exams on the 8th of May, on the week of the 8th of June. Yes.
And when again is our classes end?
Sorry?
When again our classes end? I didn't get this.
Well, I mean, the university in principle, the classes in the university end next week. I don't know if they changed this because of the fact that you started your courses, the courses later. I mean, I don't mind teaching you the week after this one. It's not a problem for me. So what did they tell you in the masterclass, that it will end on the 8th of June?
No,
on the 29th of May.
Classes end on 29th of May.
Okay, this is not the standard schedule of the university. Well, the university classes end on 22 of May. Okay. Now we might have a course on the 28th of May if you want. So I'm happy about that. Probably you will need such a course at least for the exercise session. So maybe you could have I think there is an exercise session class to recover, because at the very beginning I was teaching various exercise classes. So maybe Tomas can actually if you want to finish the exercise of the last set of exercise, we might take a day, we might take an exercise class on the 28th of May. Is that okay with you, Tomas?
Yeah, no problem by me. Yeah, I don't think we'll do all of exercise 3 today, all of the problem set 3 today. So it's fine by me to do on the 28th.
Okay, so let's then reserve an hour or two on the 28th to finish the exercise 3. By the way, let me mention that the third set of exercises and the full set of notes, it's now available on Moodle. So all the exercises are now available and all the whole polycopier is available. So everything you will need for the exam is in this set of documents. So so next Thursday is a holiday, so there is no course. And on the 28th, you will have an exercise session. I might take, depending, I want to finish this story of Morse theory today because I think it's a kind of good way to conclude the course, and it's really one of the most beautiful results I think in this field. In a sense, it's the result that started the whole field of topological field theories. So we can explain it now in detail. I hope I will have time today. If we didn't have the time to cover it completely, we can still take some time on the 28th, okay? So then we can fix the exam for the week of June, of June the 8th. Is that okay?
Yes.
It's okay for everybody to have the course, the exam on the, I mean, I don't know how many of the people there are taking the exam. At least 3 or 4 people are taking it. So is the, say, can we do the exam, say, on Thursday, 11th of June, so that we fix it already?
For me, it's okay.
Anybody has, yes? Is that okay? Okay, so let's do it on 11th of June. So as I said, I will send you the exercise. There will be 2 exercises. I will send you the 2 exercises in a tech note by email. And then, you know, you should receive it in the morning on the 11th of June. And then you can send it back to me by Friday morning, okay? So we will have plenty of time. This is not a difficult exam. I don't think that the fact that I'm giving you plenty of time is not because it's difficult. It's just because precisely I want to make sure that you are able to do the exam correctly. Okay?
Okay.
Okay.
Okay, good. Okay, so then see you in 5 or 10 minutes, okay?
See you.
So we are now going to use all this information to deal with Morse theory, properly speaking. So in order to do that, what we have to do is to put the theory on a general Riemannian manifold. Okay. So we put, yes.
Can you
yes?
put the screen? I think the screen is not completely. We cannot see the full screen.
Can you see it now?
Yes.
Can you see it?
I think yes.
Okay. So we want to put the SUSY quantum mechanics model on a general Riemannian manifold. This is actually quite easy to do. You just have to be careful with the indexes. So I'm going to use notation from general relativity. And okay, this part of the course, I will assume that you know something about the rank of homology and differential operators and so on. So this is not crucial, and this is one. I mean, if you don't know about it, the exam won't. In the exam, I won't use it. But for those of you who know this, I hope you will enjoy this part because it's very beautiful. So the metric, I'm going to denote the metric by Gij. in local coordinates. Which I'm going to denote by xi, okay? So the way to do supersymmetric quantum mechanics on a general Riemannian manifold is to first work in local coordinates, and then you have to make sure that your quantity is generalized, but as you will see, this will be an easy consequence of the geometry, okay? So this is my setting, then a general Riemannian manifold, which I'm going to call M. And then the momenta, the momenta and the coordinates are going to have the standard commutation relation. So Ij, and then I have to be now a little bit more careful if with the indexes. It's just a question of being careful with the indexes. So psi I plus and psi j minus, I have two up indexes, so I better use something which is covariant, so I will use the inverse metric, okay? So now these two fermionic operators anti-commute to the metric, okay? Now let me start by doing everything with h equal to 0, okay? So I'm going to use the formula. So the strategy is I'm going to use the formula I used before for a general, for Rn. I will make everything local and make sure that everything is covariant in an appropriate way. So notice that Pj is a contravariant vector, okay? And then I will, or maybe a covariant, I don't remember already, but it has just the opposite, the indices are down and the indices of the coordinates are up, okay? So if I put h to 0, then these coordinates are very, these supercharges are very easy, are just plus minus pi, okay? So these are scalars in the manifold, which is fine. Now I want to remember for you that C minus I is equivalent to dxi. So in local coordinates, this is completely equivalent. Remember that there was this important isomorphism between the Grassmann algebra and the algebra of differential forms, and this extends to this more general case. So we are working on local coordinates, and then we can do this locally. But you notice first of all that immediately this operator is going to be able to have a global meaning, and this is just because you see when you represent this algebra, as I said, Ci minus takes the meaning of dxi, but then Pi takes the meaning. Of course, this we know very well from quantum mechanics, of minus I dxi. So this operator is actually minus I dxi dxi. But this operator has a name in differential geometry. Is up to this factor I is the Rand differential. So we have seen many often that supersymmetric transformations act like differentials, and this is a clear case where this is what happens. Okay. So sorry. I didn't want to put here. This is just for Q minus. Okay. This is just for Q minus. But now Q plus, it's very easy because Q plus is the adjoint of Q minus. So this is I the adjoint, and the adjoint, it's also a very well-known operator, because the adjoint of the scalar operator can be constructed with the Hodge dual. So remember that the Hodge dual, it's an operator which maps P forms on M into omega M minus P forms on M. So the rank operator is an operator and has an adjoint which is given by this. So this is really very nice because now we have, first of all, we have geometrized our operators and we have given them a global meaning. And of course, let me mention that now the Hilbert space is very simple. You know, in Rn, the Hilbert space was L2, or in Rn, here we have L2 of Rn, which C to the 2n. But in a general manifold M, which I'm going to assume here, by the way, this is to be compact. So I'm going to assume that this manifold is compact just to avoid any problem with this. Then, you know, square integrability is not relevant because everything should be finite. So this is the algebra of differential forms with complex coefficients of a basis of the differential form. So the natural Hilbert space for this supersymmetric quantum mechanical model is just the complexified space of differential form. And then the last step is to interpret the Hamiltonian, but the Hamiltonian is, we construct it in this way, is the anticommutator of Q plus Q minus. And then what does it become? It becomes, you know, D dagger plus D dagger D. And this has a name in geometry. This is 1/2 the Laplace-Beltrami operator. So you see that it's really very beautiful. So Q minus becomes the Derrand differential acting on forms. Q plus is its adjoint, which is D dagger, going from E plus minus M to omega P, let me write like this, P minus M. And the Hamiltonian, all this, of course, up to prefactors, is the Laplacian acting on P forms. So you see, it's a beautiful dictionary between physics and geometry, in which the scalar supercharges of the Hamiltonian become natural operators on M. Moreover, what is a supersymmetric ground state? Well, a supersymmetric ground state is a form, because our Hilbert spaces are forms, is a form such that delta of F phi is equal to 0. Okay. But this has a name, it's called a harmonic form. Okay. Moreover, the fermionic number now corresponds to the degree of the form. Right? Because F counts the number of xi's, but the number of xi's is the number of the x's, so F corresponds to the degree of the form. So a supersymmetric ground state with fermion number equal to P is a harmonic form of degree P. Okay. So that's my second piece of the dictionary. And remember, of course, that delta phi is equal to 0 if and only if it's closed and co-closed. So this is, remember that one of the things that we proved was that a supersymmetric ground state, so a state of, an eigenstate of the Hamiltonian with 0 energy had to be annihilated by both supercharges. So this corresponds to this statement, which is a standard statement in the Derrand theory and Hodge theory, that a differential form is harmonic if and only if it's closed and co-closed. So this is again, so the two statements are completely equivalent in this setting. And now, what we want to do very often is to count the number of supersymmetric ground states. So the number of SUSY ground states with fermion number equal to P is the number of harmonic forms of degree P. The number of harmonic forms of degree P is a basic topological invariant of the manifold, which is called the Betti number. Okay, so you see, this is the way in which topology starts appearing. And finally, the Witten index is what? Well, the Witten index, remember, was the number of bosonic, supersymmetric bosonic ground states minus the number of fermionic SUSY ground states. But what is this? Well, this is the sum of P even, BP. So the sum of even Betti numbers minus the sum of odd Betti numbers. And this is very well known. This is the Euler characteristic of M. So you see that I was telling you that the Witten index is topological, and you can see it here why I was saying this, because in this particular realization is topological. I mean, literally topological. It's just the Euler characteristic of the manifold M. So that's very beautiful, and that's very nice. It's a very nice dictionary. Now, can we say something interesting with this dictionary? And yes, we do, we can. And the reason is that all these considerations were for H equal to 0. But let's now turn on H. Let's now consider the same setting when H is different from 0. Now, if H is different from 0, everything that I have just defined is going to get deformed, okay? So now Q minus, for example, the supercharged. So now if H is different from 0, the supercharged Q minus is going to be given by psi I minus Pi minus I DIH. But again, if I use my dictionary, what is this? This is DXI. This is minus I DI. And this is minus I DIH. So this is an operator acting on forms. How is it act? It acts by, first it takes the run differential, and then it multiplies it by the H, by the differential of H. So this is this operator geometric. Okay, it's a deformation of the standard run differential. And it's actually the formation that you can write in a very nice form, as was noticed by Witten in one of these papers that I mentioned. It can be written as a conjugation by a real exponential. So it's very easy to see that is this operator here. So you see, this takes a differential and then multiplies by the H, but this is the same thing as multiplying the form. If you add with, very easy to see that if you add with this on a form phi, well, we'll get minus H, then you get D of EH, so which gives me EH DH phi plus EH D phi, okay? So you see that the EHs disappear and I get precisely D phi plus DH times phi. So this is exactly what I'm writing here. So this is, sometimes I will call this minus 1 DH. So it's a deformation of the standard run differential. Now Q minus, it's just the adjoint of this. And you can see that this is I, and the adjoint of this is e to the h, the adjoint e to the minus h, okay? So let me call this E d dagger H, okay? So that's, so we obtain a deformation of the standard cohomology, but it's clear that if I, it's clear that because of writing this in this nice form, it's clear that all the properties of the cohomology are preserved. So in particular, these operators are still nilpotent, for example, right? Even after including 8, these are nilpotent, and this is obvious when you write it in this way. So dh square is 0 as well, okay? And d dagger h is also 0. So we could define a cohomology using now dh instead of d, where h is a general Morse function. But of course, the cohomology that you would obtain in this way is completely isomorphic to the cohomology that we would obtain in the previous way. Because you see, if xi, for example, so let me just say this. So the cohomology that you would obtain with dh on M is identical, isomorphic to the cohomology that we obtain with the standard differential. And this is very easy to see. For example, if psi is closed with respect to the all differential, then we can create a differential form, which is obtained by just, make sure, yes. I just create this form, which is the previous form times a function, which is an invertible function, by the way. And then, it's clear that dh psi h is actually 0. So it's closed under the previous form. And similarly, if you find a form which is exact with respect to the new cohomology, the rank operator is going to be related by this multiplication to a form which is exact and so on. So the two cohomologies are completely equivalent. So we could study all the properties of the manifold by just using this new operator. And this is realizing the fact that deforming the theory by H shouldn't change things, and so in particular shouldn't change the cohomology. So why is this interesting? So this is, you want a kind of more mathematical picture of what happens when you introduce a non-trivial, when you deform the previous theory by H. But let's now look at the Hamiltonian. What is the Hamiltonian that you would obtain? Well, if you work with coordinates, you would get something like this. I mean, you just make everything covariant in the previous expression. So this is the square of the momentum. Then you would have this. So this is the derivative of h to the square now with appropriate covariant indices. And then here I will have this operator. So here nabla are covariant derivatives. So this is a covariant derivative. And here I have this bracket. Okay. And remember that again, C minus and psi minus and psi plus have the interpretation. This can be interpreted as multiplication by dxi, and psi plus of g can be interpreted. Actually, it's very easy to see. Again, I mean, this I forget to say, but remember that psi plus has the interpretation of when multiplied by p has interpretation of the adjoint of the adjoint differential. But actually, you can see that psi plus j has the interpretation of a contraction, okay, with a vector field. So it can be seen that this is contraction with the vector field dxj. So I remind you that dxj is an operator which adds on p forms to give minus p minus 1 forms, and it's just it just evaluates the first entry, morally speaking, of the differential form with this vector field. Okay, so this is my Hamiltonian, and what a very interesting thing is that ground states, SUSY ground states of this Hamiltonian are by the in one-to-one correspondence, oops, with harmonic forms. On M, okay? So this is just follows from what I said before. I mean, this Hamiltonian, by the way, just let me make sure that this Hamiltonian that I wrote is actually just dh d hat h plus d hat h dh. So this is the Hamiltonian that is obtained by acting with, that is obtained by using the deformed Rand differential, okay? So this is obtained by the deformed Rand differential. So you can define a harmonic, you can define the analog of a harmonic form for this new Hamiltonian. And then you will find H deformed harmonic forms, but by the argument I made before, these are in one-to-one correspondence with the standard harmonic forms, because all these operators just conjugating by e to the minus h. So the harmonic forms of this new operator, the H, are in one-to-one correspondence with the ordinary harmonic forms. On the other hand, we know that these harmonic forms with respect to the H are supersymmetric states of this Hamiltonian. Okay. So what do we know as physicists? Okay. So imagine that you want to solve this problem as a physicist. Okay. Well, what we will know is that we know two things. We know that calculating the exact supersymmetric states is not so easy. Okay, because of this subtle phenomenon that there could be non-perturbative corrections to the energy of the states. But as physicists, we can do very easily a calculation of approximate supersymmetric states using perturbation theory. And we know that this is just an approximation. But what does this approximation say? So let's use let's do an approximate calculation with this H of supersymmetric ground states. Well, this is really what we just did before. I mean, this is what we did in the first part of the course. So this approximate calculation tells me that an approximate supersymmetric ground state, it's a critical point. So an approximate SUSY ground state it's a critical point of H. Okay. So critical points of H are in one-to-one correspondence with approximate SUSY ground states. And the fermion number of this is actually the Morse index. Okay. So let's denote MP the number of critical points with Morse index mu I equal to P. Okay. So this is what our approximate calculation would give us for the number of harmonic forms of degree P. So as we said before, MP is the result of an approximate calculation in which we might be overcounting ground states, but we are not undercounting. So the first thing we deduce is that MP has to be greater or equal than BP. So this is what our physical reasoning tells us. And this is actually one of the Morse inequalities. So this is something that you actually prove in Morse theory. You prove that the number of critical points with Morse index P has to be an upper bound on the Betti number of the manifold. And here we have deduced this just using a purely physical reasoning, okay? That's the first thing. Now, the second thing we know, so that's the first thing that we deduce. Now, the second thing that we deduce, the second thing we can do as physicists by doing these calculations is we can calculate the Witten index. So the Witten index is not sensitive to this approximation. So it still captures correctly the number. So we calculate actually the Witten index of this. So on one hand, the Witten index of this is the Euler characteristic of M. On the other hand, we know that this is the sum over critical index over critical points of -1 to the Morse index. So these two things should be equal. And this is this quite beautiful result in which we equate the Euler characteristic of M to the sum of signs associated to the critical. So this is another basic result of Morse theory. Okay, so you see, essentially with no effort, we have rederived Morse theory from this framework. So let me give you an example of how these things work. Okay, so these are examples that you will find everywhere. But I want to emphasize that we have a physical interpretation of this in which this is a Witten index. So let's do the calculation. Let's do an illustration of this equality for a very simple manifold, which is the sphere. Okay, so actually I think I have already done the drawings before, so let me show it. Okay, so here it is. So let's assume that we have a sphere, and let's take as a Morse function. So we have the sphere in 3 dimensions, and we take as a Morse function the height of the sphere. Okay. So this is a Morse function because it has 2 critical points, which are the North Pole and the South Pole. The South Pole is clearly the minimum of the height, and the North Pole is the maximum. So there are 2 critical points, and they are both non-degenerate because the height decreases in all directions in the North Pole and increases in all directions in the South Pole. So what is the Morse index of the North Pole? Well, the Morse index of the North Pole are the number of eigenvalues of the Hessian, of negative eigenvalues of the Hessian. But it's clear that the North Pole, any direction gives you a decrease of the height, so there has to be 2 negative eigenvalues. Okay. Now, for the South Pole is the opposite. There are two directions in which the height function increases in all directions, so it has to have positive eigenvalues, so the Morse index is 0. And now we sum -1 to the 2 plus -1 to the 0, and we obtain 2. Okay, we obtain the right Euler characteristic of the sphere. Okay, so that's an illustration of how you would do the calculation in Morse theory. But of course, you know, not all the spheres are so nice. We can deform the sphere. We can deform the sphere with this form of the boomerang. For example, we press on the sphere, so it has this form here. And when we do this, we are going to generate new critical points. So you see now, the number of critical points is not an invariant, right? I mean, you can just change the shape of your manifold, or you can, you can change different aspects of the theory. You will get new different critical points. For example, you could change H, and you will get a completely different number of critical points and a completely different set of critical points. But Morse, the results we have obtained say that this sum of -1 to the mu I should be invariant under all this. So let's see how this goes in this example by using again the Hayes function, but this deformed version of the sphere. So you see, now we have two critical points with Morse index 2, one critical point with Morse index 0, because there are like two increasing directions, and one critical point, which is what is called a saddle point. So the Hayes function increases in one direction and decreases in the other direction. Okay, so this is a saddle point, and it has Morse index m equal 1. So now you calculate the Witten index or the Euler characteristic, and what you get is again 2. But you see, what happens is that two new critical points have appeared, but they appear with opposite sign in the Morse index, and then their contributions cancel in the final sum. And this is exactly what we had seen in the context of supersymmetric quantum mechanics. Remember that we saw that in supersymmetric quantum mechanics, you might deform your function, but you might deform your potential, for example, but then ground states can become excited states and vice versa, but they always do it in pairs. So they cancel in the calculation of the Witten index. So this has a very nice analogy here, which is the case of the Morse theory, in which indeed, if you deform your manifold or you deform your function, new critical indexes, new critical points will appear, but their contribution, they will have to appear in pairs, and they will have to cancel when you do this calculation. Now you can do more complicated calculations of this story. So here we are. So you could, for example, do a calculation. You can amuse yourself by doing calculations of Euler characteristic. For example, you now take a torus, right? So if you want to use Morse theory here, again with the 8 function, you will have two points here and two critical points here. So this has m equal 0, this has m equal 2, and this both have m equal 1, right? So now the Euler characteristic is -1 to the 2 plus -1 to the 0 plus -1 to the 1 plus -1 to the 1. So this is 0, which is the correct Euler characteristic of the torus. Okay. So that's a physics derivation of two basic results on Morse theory. And now the question you can ask is the following, which is a very important question, is, okay, so far we have been able to rederive results in Morse theory with using physics, but can we improve on Morse theory using physics? And this was one of these main insights of Witten in that paper. So what is, I'm not going to get into this because that would need additional technology. But that's for me kind of the main example of how you should use the physics in relation to mathematics in this context. So remember that the main problem, what you could do in order to improve this is, okay, we have done an approximate calculation of supersymmetric ground states, and we have found these things. But it's clear that this is not an exact calculation because we are overcounting ground states. And what happens is that some of the ground states that had zero energy in perturbation theory could get a tiny non-perturbative energy by essentially tunneling effects. Okay? Now, in physics, we can do actually calculations of these tunneling effects. So in principle, what this physical picture tells you is that if you would improve your calculation of the approximate ground states by taking into account tunneling, you would actually improve on Morse theory. So if you now look at all these critical points, it's clear that not all of them are going to be true ground states. So for example, let me go here. Let me go to this example. So here in this example, it turns out that these 2 points are actually true ground states. And this gives you B0 equal to 1, and this gives B2 equal to 1, which are the two, these are the two Betty numbers, correct Betty numbers of the sphere. Now here, it's clear that some of these states are actually couldn't be true ground states, because we know that B2 is equal to 2. So one of these ground states, not these 2 states can be ground states, and clearly B1 of the sphere is 0. So this approximate ground state that we found with Morse index mu equal 1 cannot be an exact ground state of the theory, cannot correspond to the ground state of the theory. And the reason why this is not, this state cannot be a true ground state, and why not these 2 ground states can be ground states, is because of tunneling. Okay, so essentially this state can tunnel to this one and to this one, and then you can see that out of these 3 states, only one linear combination is actually a true ground state. And you can see that, you know, it's like in the double well potential. I mean, you know, you have 2 ground, you know, you have 2 approximate ground states, but you know that only one linear combination of these 2 approximate ground states is the actual true ground state. Okay, so there is so you have, like, say, you know, minus and plus, so you know that only the symmetric combination is the true ground state. Now the antisymmetric combination is actually not a ground state, it's an excited state. So something similar happens here. It's a very beautiful application of ideas of tunneling in quantum mechanics, that not all these critical points are correspond to actual harmonic forms, and the reason is because of tunneling, because not all these states are actual ground states, and only special linear combinations of them are actually good ground states. And if you do this systematically, then you discover a new so if you incorporate this tunneling effect systematically, you get a homology theory which is called sometimes Morse homology, or so this idea of using tunneling, well, this tunneling is a physical notion, but in mathematics, you can implement this mathematically by considering trajectories connecting the critical points. And this idea of refining Morse theory by using trajectories connecting the critical points was known to SwissMAP, apparently. So sometimes this is called Morse-SwissMAP homology. But essentially, the person who actually put forward this theory was actually Witten, using this physical intuition. So this is also sometimes called Morse-Witten theory. So as I said, the idea of this Morse homology, or Morse-SwissMAP homology, or Morse-Witten homology is that you can improve the counting of supersymmetric ground states by taking into account instanton effects. And this leads you to a refinement of Morse theory. So out of all the critical points, you have to really find the ones which have true zero energy by using instanton methods. And instanton methods in quantum mechanics is something that we really in physics understand quite well. So you can do this Morse homology, you can do this calculation quite precisely, it's actually even easier in supersymmetry quantum mechanics, and then you get this refinement of Morse theory. So, I think this illustrates very well the kind of moral of the course, that you can use methods of supersymmetry to understand, to rederive, mathematical statement. You actually get some sort of understanding of why this should be true. I mean, if you have followed all these physical arguments, you sort of now understand why, the Euler characteristic of a manifold can be computed by looking at critical points. Because physically, this is just because this is computing a protected quantity in the theory, and then we have to be able to do it by reforming with a function, and this leads naturally to the notion of approximate ground states and so on. So first of all, we can rederive all these no mathematical results, but more importantly, you can use physics to actually improve on this. And this idea of tunneling, for example, it's not so obvious to come with if you are a mathematician. If you are a physicist, it's almost obvious that this is what you should do with this type of Hamiltonians. And then, using this insight from physics, you can actually improve on this mathematical framework, and you can obtain a new theory. Okay, and so this is how the story of Morse theory went after Witten introduced this point of view. Okay, so I guess this is a kind of good point to stop to end the course. So if you have questions, please go ahead, because I have to leave in 10 minutes or 15 minutes. Yes.
Do you know if the videos for the last few courses will be on YouTube?
Sorry?
If the videos for the last few courses will be on YouTube?
I guess from the last two courses, from the last course, yes. For the other courses, unfortunately, there were like some problems, and there won't be, but there will be notes.
Okay, thanks. Mm-hmm.
Any question? So I hope you have made the connection, because essentially the whole course has been dealing with these ideas of invariance under deformation, how quantities in physics which are invariant under deformation can have a topological meaning, and so on. Of course, eventually we could, if I had to continue this course, I would actually explain this Morse homology more explicitly by introducing instanton techniques and doing the calculation. Now, for those of you who are interested in the topic, you can, using these math-equivalent formals that I introduced, it's very easy to actually write down Lagrangians which represent topological quantities in different topological field theories. So these math-equivalent formals can be extended. We define it in a quite general frame, and using these formals, you can write actions for theories in higher dimensions, and you can, for example, reformulate supersymmetric quantum mechanics in that language, but more importantly, you can do all important topological field theories in this language of math equivalence. So now that with understanding you got from the course on math equivalent formalism, you could easily understand the generalizations to the infinite dimensional case, which happens in topological sigma models or topological Yang-Mills theory and so on. So also we didn't cover everything in the course, which is important. I think with this base, you should be able to understand better the literature. No questions? Well, you can always ask me questions by email before the exam. But in the exam, I will really test very basic things. So if you are not familiar with either, supersymmetric quantum mechanical calculations or with all the geometry that I have introduced, this will not be what I'm going to test in the exam. So, so I'm going to really test a kind of very basic knowledge that I introduced. Okay, so if there are no questions, well, I will not probably see you for this course anymore. So next week, in 2 weeks, you will meet Thomas on Thursday for the exercise session to finish the last exercise sheet. And as I said, you have further questions, please send me an email.
Marcos, the next week there is no course?
No, because it's the next week is a holiday, Thursday.
Ah, okay.
So there will be this extra course for exercises in the 2 weeks afterwards. I mean, if you want to have a course, if you really are thirsty for knowledge and you want to have a course, I don't mind, to give you an additional course. As I said, I can. The thing is that if I really want to do this Morse homology properly, I will need at least two or three courses, because I have to introduce first instant techniques. So this is in a sense an easy point to finish the course, because if I want to go beyond this, I have to either explain Morse homology, which I think would be the nicest thing to do, but then I will have to introduce instanton calculus and supersymmetry to mechanics and so on. Or I could, use the math equivalent formulas to define other topological field theories like topological sigma models or topological Jamnier's theory. That we could also do. But this would remain very formal, because you see in topological field theory, there is the question of constructing the theory, which is based on all these ideas of supersymmetry, exact Lagrangians, and so on. But this doesn't tell you much about. I mean, this is nice. You can do this construction, but the question is, what can you get from these topological field theories? And in order to get something, you have to use physical techniques, like for example here, instanton techniques, in order to get new results. So I could tell you about topological sigma models, but I would just define them. This is okay, this is useful, but if you really want to go beyond that, you would have to, for example, use techniques of physics to actually solve topological sigma models, or use techniques of physics to solve topological Jamnier's theory. And this requires really a lot of knowledge from physics. So I would say that the natural thing to do would be to continue with this discussion of Morse theory. So if you win, I mean, I think we didn't have two courses at the very beginning of the semester, because you went to Zurich to take some other class or something like that. So if you want to have 1 or 2 extra courses on continuing this discussion, I will be happy to do it. And this won't enter into the exam. So just think about it, and if you want to get more, you can get more.
Okay. If the people want,
Maybe you can discuss it among yourselves, and then and then, as I said, this, I would have to introduce some sort of additional techniques and so on. So, or you can also read about it. I mean, it's not so complicated. I mean, now I think you have the actual, but of course it's easier if somebody teaches you about these things. I mean, as I said, discuss among you, and then if you really would like to have an extra course with more material, I will be happy to do it.